Today's note is going to be on valence shell electron pair repulsion theory, or VSEPR theory for short. VSEPR theory was first developed by Ronald Gillespie from the University of, actually he started at University of Southern California and then moved to McMaster University, and actually was one of my former profs at McMaster. A great teacher. This guy really knew his stuff. He came up with this simplified way of trying to figure out the three-dimensional shapes of molecules. And it's really quite simple to understand. It's just a matter of memorizing a few basic shapes. The main idea is that electrons try to orient themselves in three-dimensional space around an atom in such a way that they minimize their repulsion from each other. And so because electrons have that spin-up, spin-down configuration, they tend to pair up. And so it's the pairs of electrons that create bonds or lone pairs in a molecule. And so what we see is that these pairs of electrons try to orient themselves in three dimensions so that the repulsion between them is minimized. Okay. And we use that to, as I already said, determine the molecular shape, and then, of course, the bond polarity, the molecular polarity for the molecule as a whole. The assumptions that are made by the VSEPR theory are as follows. First of all, atoms in a molecule are bound together by electron pairs. These are called bonding pairs. Now, single, double, and triple bonds, even though double and triple bonds have more pairs of electrons creating the bonds, they're considered a single VSEPR pair. Double bonds occupy more space than single bonds. Triple bonds even more space than double or single bonds. Some atoms in a molecule may also possess pairs of electrons that are not bonded. Okay, these are called lone pairs or non-bonding pairs, and they count as one VSEPR pair. Since they're negatively charged, the electron pairs are trying to get as far away from each other as possible just to minimize that repulsion. The other thing is that lone pairs, we need to understand, occupy more space than bonding pairs of electrons. All right, so the first thing that we need to understand about VSEPR theory is that it generalizes any kind of a molecule. So what we do is we have these letters that represent central atom, satellite atoms, and unbonded pairs. So first of all, the A represents the central atom. The X represents those satellite atoms, the ones that are attached to the central atom. And then the E represents the lone pairs of electrons. All right, here you go, the shapes. AX2 is the first one. It's the simplest. Basically, three atoms bonded together. They're 180 degrees apart from each other. And so bond angles are 180 degrees. And it's the simplest of the structures. Then we go to AX3. And this is a trigonal planar conformation. Bond angles 120 degrees away apart from each other. BF3 is an example of this one. If we replace one of these with a pair of non-bonded electrons, then we get a bent shape where, because this non-bonded pair now takes up more space, you'll notice that it's not 120 degrees between these anymore. It's now 119.5 degrees. Okay, we call this the AX2E configuration. All right, so that takes care of the AX2 and AX3 families. The AX4 family is the next one. This is where we have the tetrahedral shape. So the bond angles are 109.5 degrees from each other. We're familiar with this one already from grade 11. If we remove one and replace it with a lone pair, we get the trigonal pyramidal shape, so that would be AX3E. And again, the lone pair takes up more space, and so now the bond angles become 107.3 degrees rather than the 109.5. We replace another one with a lone pair, and we get the bent shape, the AX2E2. This is kind of the water molecule. So 104.5 degrees is the bond angle here. And then we move to the, after this one, we move to the AX5 family. The AX5 family, now we start extending things out. We call this a trigonal bipyramidal shape. And for some bizarre reason, the trigonal bipyramidal shape leaves the up and down as being stationary. So when we remove a bonded pair of electrons and replace it with a non-bonded pair, now we get what we call a seesaw effect. All right, so it's the ones that are in that trigonal planar region in the middle that seem to get replaced in this family. All right, so the seesaw shape, again here, we replace this one. And if you look at it, the seesaw, this is your set base fulcrum for the seesaw. These two are the seats on the far end, and they kind of tip back and forth. Replacing another one with a lone pair, we get a T-shaped molecule, the AX3E2. And then replacing the last one, we get the AX2E3, and that gives us a linear conformation. All right, so that's the AX5 family. The AX6 family is the octahedral. This one does weird things. It's not like the AX5 family where we replace the ones in the plane. We actually start with the end ones with the AX6 family. So AX5E becomes the square pyramid. Upside down, you can see that a little bit clearer. But there is a lone pair down here, which kind of leaves these in a plane, and is up to form the tip of the pyramid. Replacing the other end, we get the square planar conformation, which is AX4E2. And now we can start replacing the ones in the plane. The AX3E3 conformation is a T-shaped molecule. And then the last one, the AX2E4, is a linear shape again. All right, and so that's the range of the molecules that we're going to study. We're going to leave it at that, and these are the questions in the textbook, page 236 and 237. Have a work on those. If you're going to be in class, you're going to get your hands on some model kits here, and we'll spend some time kind of working through some of these model kits. If you're doing the homeschooling, as it were, then you'll need to figure out something. Marshmallows and toothpicks, I think you can get those from the grocery store to build some of these model kits. You'll need to practice building some molecular models here. There are kits you can get through Amazon and online to buy, but and actually it is an investment because there are some chemistry classes in university where you will need model kits, and if you take any of the upper year courses, it would be an investment. If you're only going to end up taking first year chem, you can probably get away without them. It would be handy though, because you're going to cover this stuff again in first year. Okay. All right, so have a work at those, and I'll answer questions in class.